All right, hello again. So our first speaker this morning is going to be Mike Zolensky from NASA Johnson Space Center, and Michael is going to talk about past sample return missions and their major achievements.
Got it. Okay. Great. Okay. Well, thank you for inviting me. This will be a pretty overview of the sample return missions for the past 60 years. I want to talk briefly about advances in our capabilities to analyze these samples since the 1960s, and then kind of a brief summary of past sample return missions. In some cases, I'm talking about major unanswered science questions from these missions, and that's my opinion, so I'm very opinionated, so it may not be your opinion. And then even more so, the final lessons learned from these missions, in my opinion. So I work for NASA, so I can't say too many nasty things about NASA, but there'll be a little bit of that going on, I'm afraid. Okay, so this is a slide put together by Andrew Westfall at Berkeley, just showing some of the advances over the years from the 60s to present of techniques. And as you imagine, for elements, mineralogy, imaging, isotopes, the amount of sample required, which is basically shown here in area of being analyzed, has decreased dramatically. Probably least so for organic analysis, in my opinion. There's still a lot more we can do there. And since we're often going to organic-rich targets, that's really important to do. But we're down to looking at atoms in some cases. And so rather than go through all these techniques one at a time, I'll just give you just one example of changes really in my career. And that's looking at bulk analyses back in the 60s when it was clear getting the samples back from the moon. And we really did go to the moon, by the way. That wasn't faked. It wasn't filmed in a warehouse in Arizona. And here at Johnson Space Center, they built a laboratory for the initial analyses of the samples. And this building was just torn down, by the way. It's now an empty field. It's really sad. But one of the things they did was realize to do trace elements at that time, they used neutron activation analysis, which involved taking a sample, dropping it into the core of a reactor for a while, pulling it out, and measuring the gamma rays coming out to then get some idea of some of the elements in there. And so to lessen the background, they, under this building, they built a 70-foot depression under the building, which is way below sea level. So sea level is about 10 feet under this ground here. And down there, they had a special laboratory with World War I battleship steel plates cladding the lab. They had dunite, which is low in potassium, filling up the space between the steel. And they had this gigantic cesium iodide detectors, and the samples were, you notice these guys are wearing, another advance in the years, all technicians they're crew-cut white guys wearing bow ties and white jackets, right? That's another major advance in over the years, as that's all changed, thank God. Anyway, you lowered the sample down over this gigantic, like a Volkswagen-sized detector, and then measured the trace elements that way. By the time I showed up at JSC a few years later, we're measuring interplanetary dust particles one at a time. We built a detector here. It was a germanium detector, about the size of a small refrigerator. And you put the sample little grain, which is only a few microns across, on top of the detector, and then measured the same technique. First you put it in the reactor, brought it back. Now it's radioactive, it's transmuted. You're looking at the prompt gamma rays from that. But the detector is a lot smaller, about the size of a cell phone. And even that's now gone. And so when the Hayabusa 2 samples came back, the technique they used was to look at muonic X-rays. They had a detector. They have a laboratory here about the size of the Caltech campus, making the world's most intense muon beam. They radiate the sample, maybe it's milligram-sized sample with muonic electrons that creates muonic atoms, which then they measure the lifetime of those atoms. They give off an X-ray. And basically you can look at the entire periodic chart on your sample, way sub-gram size sample, and it's non-destructive. You just need a laboratory the size of this Caltech campus, right? So you're not going to put this in a spacecraft. So this is another example of a technique where you absolutely must have a return sample. But now you can do the entire periodic chart, basically, not easily, but it's accessible even to very tiny samples. So now I'm going to briefly talk about some sample return missions over my career. So the moon, we have numerous missions, Luna, Apollo, and Chang'e missions to all over the front of the moon, and then the last mission, the Chinese mission, to the back of the moon near the South Pole. And of course, the major advance from these missions, having samples, was to understand just how important the impact process was in the inner solar system, especially the Earth-Moon system. Having formulated a new origin hypothesis for the moon, which is an giant impact on the Earth, but also understanding how important impacts were in reshaping the Earth and all the inner planets and moons. That's I think, probably the major advance from lunar samples. But there's still, even after 80 years, many outstanding questions on the moon. For example, what's the nature and amount of water at the South Pole? How much is really there? The amount seems to vary from mission to mission. Was there ever a global lunar magma ocean? Probably there was, but there are still alternative hypotheses. What does the lunar mantle look like? Details of the bombardment history, including the age of the South Pole Aitken Basin, which has important implications for the water resources that may be there, and possible involvement with early life emergence on Earth. Again, bombardment history, determined only from those lunar samples, had a lot to do to tell us about bombardment history at the Earth. And also how the solar system's climate, and by that I mean solar wind, cosmic rays, changed throughout time, since the moon is a great record of that. And then what's the detailed thermal history of the moon? So even after 60 years of looking at 300 kilograms of lunar samples, there's still major questions that remained. So the sun, and here's Caltech's Don Burnett here. So we had a mission, the Genesis mission to the sun. It didn't actually land on the sun, but it basically soaked up solar wind for many months. The landing was not so successful, but the samples came back to Earth. And it's taken a tremendous effort on the part of Don and his team, but they've managed to realize really almost all the science goals of the mission. It's an amazing achievement, really. It shows you how scientists can work really hard when they have to, and they did. And another thing is that, after the samples were smashed up on landing, they had to totally redo the preliminary examination plan in real time, and that was done by the team working very closely together. It's an amazing effort. And really, as far as I can tell, the major result has been the measurement of isotope abundances in the sun. And so the reason for this mission was to find out what the bulk composition of the sun was, because really that's the major input into any model of solar system origin history, is to knowing what you started out with. And a big surprise for most people, not everybody, for most people, was that the amount of oxygen-16 was a lot higher than the inner solar system planets and moons was. And that was a big surprise for most people, not everybody, most people. And so it implies that some unknown process depleted O16 by quite a bit from the sun's protoplanetary material prior to coalescence of the inner planets. That's still kind of a mysterious process. And a major unanswered question is, what's the bulk carbon isotope abundance of the solar photosphere? Because of the contamination of the materials from the mission with organics from the Earth and soil, it's been difficult to get that measurement. And so my understanding is they're still working on getting a good number for that. Okay, largely kind of forgotten are a series of missions which collected asteroid and comet dust in Earth orbit. And you had the Long Duration Exposure Facility in the late 80s, which is the size of a school bus. It would have just barely fit into this room. It was in orbit for 69 months, and it collected thousands of impacts from not just space debris, but also micrometeorites. There was also meteorite and debris collectors on the Mir, the Russian space station, in '96, and some of those are at JSC. And there was also the Jackson-Tom-Popolo experiment on ISS, which collected micrometeorites in silica aerogel. These missions were, I think we frankly didn't learn that much about asteroid and comet dust from these missions, but you know, the requirements of these tiny samples drove great advances in analytical techniques during this time. And a lot of the people working in the field now on Stardust samples or Ryugu-Bennu samples cut their teeth on these samples. And so a lot of young scientists got their first look at asteroid and comet dust with these missions. And a lot of techniques for cutting samples in aerogel, pulling it out of the aerogel, looking at impacts into metals and foils, that all came out of, that knowledge came out of these missions. I will also say that my experience with LDEF led me to the opinion that you shouldn't have astronauts involved in collecting samples. And maybe there isn't time to discuss that. If there is at the end of the talk, I'll talk about it briefly, but I'll come back to that later on. So now I'm going to move on to asteroids and comets, and first for the non-spectroscopists in the audience, you know, the asteroids are classified based on reflectance spectra, and the shape of these reflectance spectra are quite distinct, and the asteroids are grouped in roughly into many different subclasses, of which these are the most common, especially the C and S types, which are very, very common. And based on the spectra, there's some expectation of what these asteroids might consist of. For example, the S-class asteroids thought to be stony composition, magnesium iron silicates, and the C-type, hydrated minerals, silicates, a lot of organics to give this kind of flat spectrum. But in fact, the meteorites, which should derive from these asteroids, don't usually match these spectra very well. So it was realized, you know, decades ago that there was some process modifying the surface of these asteroids, which is where the spectra are derived from, to kind of hide the actual mineralogy of the asteroid. So it was important to do missions to these asteroids to try to verify or disprove these identifications. So we've had 3 sample return missions to asteroids, Hayabusa, Hayabusa 2, and OREX. OREX is still doing the sample analysis now. So you see the amount of sample returned increased dramatically over this time. The first asteroid was Hayabusa, an S-class asteroid, and the last 2 are C and B class, and the B class really is a subclass of the C. So these are really perhaps similar to carbonaceous chondrites. This one should be similar to an ordinary chondrite, and those that all proved to be the case. And as you can see, these are also, these are not first-generation asteroids. They're from larger objects that were smashed apart, and then some smaller fraction of that original material then reaccreted, maybe with other stuff being added as well, into a second, maybe third or fourth generation asteroid. And they're pretty tiny too. The biggest one is Hayabusa, only a kilometer across. And I'll go on. So what do we learn? Well, one thing is, the space weathering history of these asteroids has revealed the surface ages, which are pretty young. And you can see solar flare tracks in olivine grain. This is from a Ryugu sample. There were space weathered surfaces on materials that were recovered. You can see radiation damage of phyllosilicates in the carbonation material from asteroid Ryugu. And so that space radiation, that space weathering, is what has been changing the surface of the asteroid and making the spectra. That's one reason why the spectra is so difficult to match to the meteorites. It also changes about composition of material, so it's driving it towards more iron-rich. So here's a ternary diagram of magnesium, silicon, aluminum, and iron. And this is the bulk composition of the phyllosilicates in this Ryugu sample, and it's being driven towards the more iron-rich corner by space weathering. So space weathering is changing the mineralogy, it's changing the composition in dramatic ways. And that was suspected, but now it's been confirmed by these missions. Another bad result of these missions is we realized that the meteorites we have changed dramatically from when they were in space. We realized that a little bit. They rusted a bit, et cetera, but all kinds of other things have happened. And the Hayabusa and Hayabusa 2 samples were brought back in nearly a vacuum container, not quite, very little bit of atmosphere bled in. And yet, even though those samples were kept at a near vacuum for the entire mission, and have been kept in a vacuum or nitrogen since then, there's still minerals growing on those surfaces because the materials are interacting with the terrestrial environment, the atmosphere. Even in nitrogen-filled glove boxes, atoms from the welding material finds its way onto the sample. Just amazing. So these are sodium sulfate crystals growing on a surface, an Aruga sample, and little flakes of sulfates here. And the meteorites we have from the analogous meteorites are even more so processed by this. And so what this means is you really have to return your sample in a vacuum, hermetically sealed. If you really want to learn what the material is like in space, as opposed to on the Earth, right, you really have to return this sample in a vacuum. That's a must. And speaking with experience from some missions, the spacecraft hardware builders are reluctant to do that. And they'll tell you, oh, if you do this, there's a good chance it's going to explode or implode on reentry. And you shouldn't believe those people. And so JAXA did a great job in building almost hermetically sealed sample return capsules. They're nearly there. So it's possible to do that. And you've got to demand that in your mission. That's all there is to it. And this also means that the meteorites have dramatically changed, which is why you have to have samples returned from objects. You can't just use meteorites. That's all there is to it, especially for organic and water or volatile-rich materials. So top-level results from these asteroid sample return missions. Well, the S-class asteroids really are verified to be the source of the urban chondrite meteorites. So the most common kind of meteorites really do derive from one of the most common kinds of asteroids. And the C-class asteroids verified to be the source of at least some carbonaceous chondrite meteorites. Perhaps they're also dead comets. There's some argument about that. It's a discussion you could have. The C-class asteroids, are verified to be very volatile-rich, including water and CO2 preserved in there. And there are food inclusions in these return samples as well. Actual samples of fluids and gases from the parent asteroid, which are analyzable on the Earth. In my opinion, the Bennu and Ryugu samples are essentially identical, really, to CI chondrite meteorites. There's some differences, but they're very similar. But because they were collected in a more clean fashion, they're much superior to the CI chondrites in understanding the solar system. And the CI chondrites are used as a key gauge to understanding the bulk composition of the solar system. So it's important to know how those samples have changed on the Earth. Space weathering was demonstrated to be very significantly altering the asteroid reflectance spectra, which was what was expected. So you have solar wind implantation, micrometeoroid impacts, vacuum thermal processing. Those are all really important. And as I said earlier, return samples were phenomenally reactive with the Earth's atmosphere. So oxidation and hydrolysis begin immediately. For example, iron 2+, in minutes oxidizes to iron 3+, and you have new minerals forming on your sample. And it happens in minutes, and it's irreversible. So once you let oxygen or atmosphere into your sample, you've already changed it. And any kind of water also makes dramatic changes. So I can't stress that point enough. Major unanswered questions. The absolute chronology of many processes is still very poorly understood for asteroids. And there's still difficulties in interpreting reflectance spectra of asteroids. For example, Bennu was presumed by the team, I'm not in the team, but as my understanding, they presumed it to be a CM chondrite, which is one kind of carbonaceous chondrite, but it proved to be a different kind. And so why did they get that incorrect and I'll go on. And, majority of asteroids still very poorly understood, frankly. And we have, 3 samples from 3 asteroids, and 2 are almost identical. And there's, more than 1 million asteroids, right? And so there's a lot more to learn there, obviously. Comets. So Don Brownlee, the PI of the Stardust mission, Caltech undergrad. And here's the best image of Comet Vil-2, the target of the Stardust spacecraft, which collected dust from the comet Coma in silica aerogel. And I'll just, as an aside, here's one of the best pictures of the comet nucleus, Vil-2 from Stardust mission. Here's a pretty good picture of comet CG from the Rosetta mission, 100 meters scale. You notice a difference in resolution of the image, right? And this is partly due to the fact that the Stardust spacecraft's camera was the coldest part of the spacecraft, and so all the outgassing from the spacecraft coated the optics of the camera. And that was a huge issue for the entire mission. And so, don't make your camera optics the coldest part of the spacecraft. That's a big thing here, right? No one realized that until after launch. Oh yeah, the problem, right? Now it's important because the Comet was actually a navigation camera used to target the Comet, so we missed it and didn't hit it during sampling. And so being able to see the Comet was really important, an integral part of the mission. So samples were collected in silica aerogel at very high velocity, which we knew would result in the melting and vaporization of a large part of the cometary grains. But from lab experiments, we knew that some fraction of the grains would survive. But we still thought that probably all the organics would get fried. So it wasn't a super important thing for the mission to clean up the aerogel completely of organics. It was also impossible to do that, in fact. We thought, well, we're not losing much because we're not going to catch much organics anyway. They'll be fried. And that turned out to be wrong. And so the collection process didn't totally destroy, but really mangled the largest fraction of the impacting grains. Probably 90% of the grains were finer material, which was mangled by the collection process. We knew that would happen, but some fraction of them made it through. For example, here's a grain. This is a 5 micron scale bar. Here's a large sulfide crystal which protected this fine grain material in its wake. So it entered the aerogel at high velocity, but didn't spin. It basically went in straight like this. And so in the wake of that, the fine grain material, which included organics, very nitrogen-15 rich organics, survived the impact unscathed, even without much heating. And that was unexpected. And here's the organic nanoglobule, a hydrocarbon bubble, which is found in most organic-rich meteorites, which survived very, very nicely in this material. So it should have been fried, and it wasn't. So we should have cleaned up the spacecraft and the aerogel more than we did. And by the way, the presence of this material requires that the comet, as expected, formed at the edge of the solar disk or beyond in a very cold environment. So be prepared for your mission to exceed expectations. Be careful about cleaning up your spacecraft. And people are doing that. Pre-solar grains. So one idea for VIL-2 going in was maybe the comet's mostly pre-solar material. We don't know. It turned out it wasn't. Okay? About the same range as in chondritic meteorites, a little bit higher. And here's the pre-solar grain. I'm going to go a little faster here. Was there liquid water on Comet VIL-2? Well, there were some carbonate and sulfides found in the aerogel, which on the Earth form in aqueous environments, but no phyllosilicates or things like that. So if there was liquid water on VIL-2, there wasn't very much. The big surprise of the mission was the presence of very high temperature phases like calcium lunar-rich inclusion, CAI, which were not expected in the comet. These appear to lack the most refractory types, some meteorites, so they're kind of low temperature, but still very high materials, both calcium lunar-rich inclusions as well as chondrules, which require dust to have been melted, fried once or twice or more. They will melt droplets then. And again, these require origin in some either by shock in the outer solar system or by some resonance near the sun. So it was surprising to find these high temperature components in the comet, to be frank. It was pretty unexpected to most people. And there's some evidence they might even had some low temperature thermal metamorphism taking place. Olivine grains, this is chrome versus iron and some olivine grains. And the Comet VIL-2, which are blue here, the compositions of these minor elements in the olivine are most similar to some meteorites that have been metamorphosed to 200 degrees C. So there's some indication that perhaps some of these materials saw not just melting, but also some metamorphism as well. That's going to be explored more. But so the result is that there's presence of these high temperature materials seems to require large-scale radial transport of materials throughout the early solar system, not just inward, as we knew would happen, but also some material got tossed outward. You had some heating in the inner solar system, material being fried, and then got tossed out here, then mixed with materials that formed and stayed out here in the outer solar system. So the comet is really a hodgepodge of materials from across really the entire nebula. It wasn't just a collection of materials from the outer solar system, as many people had suspected. And to questions, Joel, how representative of our Comet VIL-2 samples of all comets? We have no idea. We still have to characterize the nature and composition of that fine material, and then also how much interstellar material is preserved in comets. You determine the origin of these fine materials. Work continues there. So lessons learned, last 2 slides. First, keep your samples, especially the sample intimate materials on the spacecraft, as clean as possible. With any documentation, all the contamination very, very well. We did that to some extent in Stardust. Not as good a job as is being done now by OREX and JAXA for Hayabusa and Hayabusa 2. And you got to return your samples to Earth in an airtight container. There's just no 2 ways about that. Okay, you shouldn't accept anything less. And also, the health and safety of the samples must be the primary mission priority. So you shouldn't have astronauts, cosmonauts, taikonauts involved in collecting the samples, because if you have people on board the spacecraft, their health and safety is paramount, not the samples. And that's been shown time and again in some past missions. And appear to be more successful than you thought you'd be. Techniques that continue to evolve, which means that during long missions, and these are all long missions pretty much, you should keep your plan, preliminary analysis procedures flexible. So don't lock in the sample preliminary examination too early, and make the team membership as inclusive and flexible as possible. So you get young people on the mission and new techniques that weren't around when you launched. And finally, do your best effort to keep the sample very clean. And since it's impossible to bring back a sample probably hermetically sealed and impossible to keep it totally away from the Earth's atmosphere, you should do some preliminary analyses on the samples immediately upon recovery. You shouldn't wait for weeks while you carefully open the spacecraft and then weigh everything and then count everything up and look at things and document stuff. You should be doing some analyses from day 1, because samples are already changing while you're doing all those special things. And I'll stop there. Thank you.